Hello and welcome to Maths on the Move, the podcast from plus.maths.org. I'm Rachel Thomas. Here in the UK, we're getting settled back into school and work after our summer holidays. Now, mathematicians, like everyone else, also enjoy their holidays. And in this podcast, we're going to look at a particularly interesting holiday experience that's open to maths PhD students. In a week this July in Cambridge, the Newton Gateway to Mathematics organised the UK Graduate Modelling Camp. This modelling camp has been going since 2009. It started off in Nottingham, then moved to Oxford from 2010 to 2020, and has been happening in Cambridge ever since. In the camp, students are given real-life problems from industry, and their task is to come up with mathematical models that can help solve them. To find out more, my colleague Marianne Freiberger spoke to Chris Breward, an applied mathematician from the University of Oxford. Chris has been involved with running the modelling camp most of the times it's taken place. Marianne started off by asking Chris, what's the camp all about?
So the idea is to give the participants hands-on experience of building and solving mathematical models for phenomena that happen in the real world, really as a training exercise so that they could go on and do this on live problems further down the line. And in particular, some of the students that are coming this week will be going off next week to the European Study Group with Industry that's happening in Edinburgh.
And how does it work? So you have a week, Monday to Friday. What happens in that week?
We get the students to arrive on the start of Monday afternoon, and then they spend the afternoon listening to presentations by 5 mentors. Those presentations are about challenges that the mentors have got spanning different areas of science that the students are then going to build mathematical models for during the week. So they do that, they listen to those 5 presentations, and then they decide a ranked order of which of the challenges they'd each like to work on, and we use that data to form them into working teams, and they form into those teams. And then for the rest of the week, the Tuesday, Wednesday and the Thursday, they work in those teams to try and address the challenges that the problem presenters have brought along.
And then on the last day, they present what they've come up with.
Yeah, crucially, they'll be interpreting their results, their mathematical results, back in a way that somebody that wasn't a mathematician would understand.
And give us an example of one of such challenges.
Well, we've got 5 challenges this week. One of them is how to extract sugar out of sugarcane. So this is a problem that's been studied quite a lot at industrial maths events in South Africa. And so the students will be building a mathematical model for how liquid flows through sugarcane. Another problem, if I may, is one about the modelling of blenders and food processors. So there you might think of dropping a carrot into a food processor and turning it on. So you go from having one long carrot to having lots of little bits of carrots. How does that distribution of sizes change as you press, the longer you press the whiz button for? And so the students in that room are making a probabilistic model that says, there's some chance of the carrot being chopped in a certain place, and how does the distribution of carrot bit sizes evolve during the blending process?
And are these are real problems that people in industry are interested in? These are not toy problems designed for students.
So these problems in the main have come to mathematical scientists around the country from companies. We have a problem that Lena has brought about transport in the steel industry. That came from a conversation that she had that then involved her doing a project with a steel company in the UK. And so it's using the actual challenge that they gave to her for a long project, and she will be helping guide the students through the problem formulation and problem solution phases. Similarly, the shredded cane problem that I mentioned earlier, that came to a study group meeting in South Africa over numerous years, and we've tackled, the international community have sort of tackled various aspects of that.
And how, in your experience, do the participants respond, and what do they get out of it?
So I think the participants get a number of different things out of attending the camp. Certainly they get exposure to new ideas. That might be new scientific ideas or new mathematical ideas, but much more importantly than that, they get the experience of working in a small team of people. And quite often mathematicians don't do that. So it's a bit of a novel experience for them to come together and try and solve a common goal.
And they enjoy it, I imagine.
Yeah, I think they find it hard work. You know, we have them up in the morning and working all day, and then probably still discussing things over dinner and after dinner in the bar. But you know, when I was walking around today, there was a reasonably large number of smiles amongst the participants, and so that's a good thing.
And what is the benefit for mathematics, or for the mathematics community, if you want to call it that, of funding such an event and running it?
So I think the benefit to mathematical community of having the grad camp is that it exposes students from across the country to a problem-solving way of thinking and reduces their scaredness of tackling problems that they've never seen before. One of the great benefits of this is that we have in the UK a rich history of being at the forefront of tackling problems that come from industry. And the sister meeting, the European Study Group with Industry, that happens the week after the grad camp, it is a similar structured event where companies turn up on the first morning with real live problems that they need mathematics to help them solve. And the students can go to that and are very well prepared to then bring their skills to bear to try and tackle those problems and crucially communicate effectively with the company people that are there.
Now that we know what the idea behind the camp is, let's talk to some of the people who took part. Marianne spoke to Michael Smarr, a PhD student at the Institute for Global Pandemic Planning at the University of Warwick, to Emily Cook, a PhD student at the University College London, and to Julian Glover, a PhD student at the University of Manchester. Now, sadly, Marianne wasn't able to be at the camp in person, so she talked to them all online, so apologies for any glitch with the sound. Marianne started off by asking Michael what motivated him to go to the modelling camp.
I remember my supervisor advised me and said, no, you need to explore different aspects of mathematics to see how beautiful they are. And so I felt, yeah, I need to actually take a break from the epidemic modeling I'm doing to go to do something different. And that is one of the things that actually motivated me. And I wanted to actually see if the knowledge I have, the background I have in mathematics and in modeling, I can be able to apply that to other industrial problems. This was the first thing that actually motivated me.
And what kind of challenge did you end up working on in the modeling camp?
That it was actually a transport optimization problem for a steel company. So we wanted to see how we have different ways at which we can be able to get product from the production to the customers. And the company we actually worked for during the camp had 2 production centers and they have 2 distribution centers. And there are different ways by which you can be able to get these across to the customer if they place their orders. So they were saddled with the responsibility to design a framework that can be able to accept order from the customers and know what is the most cost-efficient way to get this product from the production to the customer.
Did you find a good solution?
Yes, we did find a good solution. Like I said from the beginning, in my team, we're kind of unfamiliar with that problem. So we spent the first day trying to understand what the problem is all about. But the first thing we did was to be able to interpret that question or the problem that we had in mind. We captured that mathematically by formulating the model. And in formulation of the module, we actually had a lot of disagreement within the group. But that was the most fantastic aspect of that conference, that program, I must say, because since we had different mathematical backgrounds, we came together, everyone wants to bring what you understand by this. So we tried to bring all the possible things we understood by the problem, and we formulated that. We took the whole day to try to formulate the problem because of different ideas and different opinions. But I realized that the more we disagree with each other in how to formulate the problem, the more closer we're getting to the reality of what we needed to do. And that's how we did. And at the end of the day, we actually got a good result to what we wanted to do.
Emily also found that discussion and disagreement was very useful. And interestingly, she also found that getting things wrong was an integral part of the process of coming up with a solution.
So I worked on the blending problem. So we were essentially modeling how a bit of carrot broke up in a blender. These blending companies, what they're really interested in is, I guess, a mixture of things when you're using a blender, but mainly how texture varies with time as you blend up a fluid. I blend up sort of carrots in large bits and how they become smaller bits. So we decided to model it probabilistically. We sort of went down a few pretty ridiculous paths to begin with. Well, not ridiculous, they were helpful, but wrong. We sort of initially considered that a single piece could be hit by the blender with some probability and it would split in half, and then each time it would be split in half and half again, which is an interesting approach. However, it sort of allows for infinite blending, and we eventually realized that with that model, we'd end up with, I think we did one simulation where we ended up with the average size of particle being half the width of a quark, which obviously isn't very realistic, and we realized we were essentially blending our carrot bits into light, which would have been impressive, but obviously it was not very useful to the blender manufacturer. So instead we went with a discrete model where we assumed that there was sort of some finite chunk which the blended bit of carrot could break up into.
Once that assumption was made, that there's a limit on how small you can make a piece of carrot, Emily's team were off and eventually came up with a good modelling approach to the problem of how to blend a perfect smoothie. Julian's group looked not at what we put into our bodies, but what goes on inside them.
I worked on lipid rafts. So if you want a bit more details, it's the membrane of cells are formed of this bilayer, so these two floating layers of lipids that are touching each other. And sometimes there's odd proteins or other molecules that will get embedded in these layers, like cholesterol, and they can make the lipids kind of behave more rigidly. And the areas where you have a bunch of these lipids agglomerated together, behaving all in this kind of rigid way, can float about and are called rafts. And even though they haven't been directly imaged, the biologists believe they may be incredibly important in mediating a bunch of important cell processes like transport of molecules, except you can't image them directly. And so instead, mathematicians come in and we say, we think they're formed this way, or let's see if chemically they could be formed like this or X, Y. And so biologists could be like, nope, that's nonsense, or hey, maybe this makes sense. And that was our goal.
Do you feel that you came up with a good solution, with a good approach?
I myself would have no idea, but our mentor, Shaker, who was lovely, said he was really impressed with us. And we came up with, we had multiple ideas, and we managed to, at the end, have a model that did form on the surface of a cell a bunch of little rafts of lipids. And so I'd like to think so.
And how did you enjoy it? I mean, how would you describe the whole experience?
It's very intense, and it's very much you're up and you're working and you're trying to get stuff done. And maybe not for everyone who was there, but myself especially, I hadn't done a lot of modeling, just straight up, just like, you have 5 days to do this. No, not even 5 days. You have maybe 3 days plus a half to get this done and get a presentation ready and be, really able to perform it with a bunch of people you've never met before. And it was really hard work, but it was really fun. I had a really great team. Yeah, fun and quite compelling is a nice is a way I'd put it. And I got to learn about some new things, but in a really guided way.
Emily agrees that it's the working together that's the most fun. And she also found that having to work together helped with forming some very important skills.
I think you learn a lot about working with people, and it's really engaging and fun to just be able to talk with people about maths and kind of disagree and have to argue your point. I think it taught me a lot about explaining my thought process to people. We only had sort of, I guess, 3 days to look at something, and it means that you do have to get very good at explaining clearly and in a succinct manner what you're trying to say. I don't know, I think that was really, really rewarding, and I felt like I learned a lot from that towards the end.
Finally, Michael really enjoyed broadening his mathematical horizons.
Something personally that I realized is that the program made me aware of myself. Yes, because all this while I've been imagining that since my research is focused on epidemic models, that is the areas of expertise, but then we are presented with a problem that is from a completely different mathematical aspect. And we spent just a day. And because of the background we had in mathematics, we're able to understand that we had a potential within us, that we can easily understand any mathematical problem presented to us. And so that period of the disagreement and agreement actually makes it more fun.
As we've heard, each of the groups in the modelling camp is being guided by a mentor, a more experienced mathematician who can spark ideas and make sure the group doesn't stray too far in a direction that's not helpful or fall down a mathematical rabbit hole. To find out what the whole experience is like for a mentor, we spoke to Ashley Hutchinson, who is currently a Royal Society Newton International Fellow. Marianne asked her what problem her group was working on.
I was working on a project that was actually first introduced by a study group that I participated in South Africa. The project is about the extraction of sugar from shredded cane, and during this extraction process, there are various issues that come up. So what we were looking at is addressing one of these specific issues and trying to see if we can come up with ways mathematically to design strategies to try prevent these issues from occurring. So what happens in this extraction process, water is filtered through shredded cane and it dissolves the sugar in the shredded cane. But often what you see is you get these massive bubbles, air-filled cavities forming, and they are impermeable, so no fluid can flow through them. And this actually leads to flooding. And as a result, factory processes generally have to shut down for sometimes as long as a day. So what we're trying to look at is to come up with strategies to prevent these air-filled cavities from forming. And the way in which we approach this is by using mathematical modeling, which basically describes a situation using equations, for example.
And what does your role as a mentor entail? And what's the benefit for you to be doing that?
Okay, so with the mentors, basically what we do is we act as an industry representative. So we bring a problem to the students. On the first day, we pretty much do a 20-minute presentation where we present the problem and perhaps give some guidance as to how the students can approach it. From then onwards, the students will then work on the problem every day, and we will be there to assist by providing some guidance or answering any questions that they may have. If they are going off on a complete tangent, we will gently reel them back in just to ensure that they do stay on the right track. But that is the goal. It's not to solve the problem for them. It's to assist them and enable them to solve the problem, or at least gain some insights into the problem. A lot of these problems are very complicated. You can't just solve them in a week. But you know, it's interesting how students actually come up with good ideas and good answers. The benefit is, I think, definitely the enjoyment of seeing people work together and coming up with good ideas. Often a group can come up with ideas that perhaps I haven't thought of myself, which is very beneficial for my own research as well. But I think it's just a really nice week, just interacting with enthusiastic students and solving some cool problems.
And then, so it can happen that students might come up with an answer that actually then goes further than the modeling camp in that it's useful for you.
Yes, in past study groups, actually, ones that I've done in South Africa, we have worked on problems that have led to publications and further studies. It's actually led to also PhD student projects. So there is a lot of benefit and reward as you progress through these study groups.
And from this past week, was there a particular highlight? You can remember anything that was striking, or was the whole experience?
I think the whole experience was really nice. I enjoyed the students in my group. I thought they were very engaging and dynamic. They were also very interesting as well. So they were quite relaxed and they were fun to work with. That made it extremely nice.
Okay. And finally, what would you say to somebody who has been asked to become a mentor, or who might be interesting and is not quite sure if that's the right thing for them to do? What would you say in order to encourage them?
They should absolutely do it. It is really a lot of fun. And the feeling that you get at the end of the week when your students present their ideas, there's really this feeling of a lot of pride. And it's nice to see people learning and being interested in a problem that you're also interested in. I would definitely do it. It's really nice also interacting with the other mentors and seeing what they work on. Met a lot of people at different universities, which has led to the discussion of further collaborations. So it is very, very useful.
Finally, before we go, we asked Julian, Emily and Michael what advice they'd give to someone thinking of attending the modelling camp next year.
Go. Worst comes to worst, it's a week of your life in which you're going to be learning some new maths and talking to some people who are your peers and your age. I think it's helped to reset my brain a little bit. You get really bogged down during a PhD, kind of going deeper and deeper into nitty-gritty. I feel a lot more refreshed, if a bit tired. I highly recommend it. I couldn't recommend it more.
I mean, first of all, do it. It is really fun. You need to go in with an open mind. You need to go in with sort of confidence that you'll get stuff wrong and being okay with that. Everyone there was so nice. Very sort of a lot of socializing and talking about unrelated projects. I think there was a really great group of people there. It was really fun. It was just really fun.
Just go up there. You need to explore. There are a lot of things you need to see about mathematics. We shouldn't just get ourselves limited to the area of research which we are into, but then be free to explore different aspects of mathematics. And the truth is that there is potential in every mathematician that we can be able to use to solve real life problems. And it is a fun program. If I will have my way, I will keep attending that program until I'm done with my PhD.
That's it for this edition of Maths on the Move. If you're interested in taking part in next year's modelling camp as a student or a mentor, keep an eye on the website of the Newton Gateway to Mathematics. The web address is newton.gateway.ac.uk. The modelling camp typically takes place in July and the deadline for applications is in the spring. And you can read more about the fascinating maths happening at the Gateway in our content on plus.maths.org/gateway. Thanks for listening and bye-bye.